Welcome everyone. Today is like officially it's the last tutorial in this subject, single degree dynamics of single degree of freedom system. But I'll be taking another kind of lecture where we'll be looking into some parts of coding as well, coding of um, the numerical methods, the central difference method, the Nigam-Jennings method, and Newmark-Beta method. Today we will focus on problem solving, and then we'll also be looking into the response of a single degree of freedom to a step function and a ramp function if time permits. So let's start today's session. I was already drawing the problem. So uh, let's directly start the questions. So here you have uh, a long 375 feet long concrete box girder bridge, and it has two apartments. I've marked the apartments, and these are you have some local beds. So these are so this is bent one and bent two. Basically, these are some supports kind of system. And this is the cross section of the bridge. Like if you cut it uh, in this direction, if you cut it in this direction and have a look at the cross section, this is what you'll be looking at. So this is the sorry, this is the cross section. You have footings. So each bent like basically in each cross section you have three uh, pillar kind of thing, and the height is 55 inch. And okay, in the question it is given that the cross sectional area of the bridge deck is 123 feet square, and the weight of the bridge is idealized as lumped at the deck level. So this is the deck level, and the unit weight of the concrete is 150 pound per feet cube, and the weight of the bend can be neglected. Each bend consists of three 25 feet tall columns. So these are the three columns, and they are of circular cross section with I, like if this is the axis, if this is the Z dash axis, this is the X dash axis. So Y dash, Z dash is 13 feet to the power 4. So what do you have to do? You have to formulate the equation of motion governing free vibration in the longitudinal direction. And it is given that E is 3000 KSI. And you have to write down the equation of motion governing free vibration. So no force is acting on the system in the longitudinal direction. So just hang on for a second. Now it's better. So, so here, when you have to write down the equation of motion in the longitudinal direction, suppose I draw the diagram of the cross section of the bridge when I cut it in the longitudinal direction. So you will have something like this. If this is the bridge, you will be looking at two bends like this. This you'll be looking at these two bends here. Then you will have the two apartments here, and like these are like fixed. These are basically like fixed columns, fixed at both the ends. And suppose now you are, it's a free vibration problem, so certain initial conditions have to be imparted. Suppose you are imparting an initial displacement to this bridge, and suppose you move the bridge to this position, right? So the column will be bent like this, the column will be bent like this. So the stiffness which will be provided in this task will be the stiffness of this bend and this bend. So, and for writing the equation of motion, what do you need? You need the mass and the stiffness. So how do I calculate the mass? So first I can calculate, I know the cross section of the bridge, and I know, what do I know? I know the length of the bridge, okay, and I know the unit weight of concrete. So first I can find out what is the weight per unit length. So what is the length? Length of the bridge is, I have to calculate the weight per unit length. So weight per unit volume is 150 pound per feet. Okay, maybe I'll give you I'll give you 2-3 minutes. You try it, and then we discuss. I think that will be a better technique. So finally, you need to write something like this. You need to find these two quantities, M and K. So what will be the stiffness of one column? So it's a fixed kind of column, fixed it's fixed at both the ends. So stiffness of one such column will be 12 EI by LQ. So So K bend will be 12 E I by L cube, and length being the height, let's say h cube, and there are three such columns in each bend, so that multiplied by 3. And what will be the total stiffness? The total stiffness K will be 2 into the stiffness of the bend, since there are two bends. This is bend 1 and bend 2. So this into 2. So 3, 12. What is E? E is 3000 KSI. So 3000. And I, what is I? 3000 KSI. There you'll have to convert the unit. You have a conversion unit of 144. This is you are converting from KSI to, I believe it has to be converted into pound per feet square. So you will have this conversion unit into I. I is 13 in 13 feet to the power 4. Uh, Unit is feet to the power 4. So 13 by height is 25 feet. So 25 to the power 3 into 2. So if you solve this, this will be 25880 kips per feet. And what about mass? Mass will be weight W by G. G is 32.2 in this unit system. I'm giving you the value of G. And what is the total weight? Weight will be 150 pound per feet cube. This is per unit volume. So 150 into it should be, you have to multiply it with the cross section to get the weight per unit length. Suppose this is the weight per unit length, and how much is the total length acting on one, how much is the total length? This is the total length, that is 375 feet. So that multiplied by 375. So if you solve this, this will be around 214.9 kip second square plus v. Number crunching is fine, but this is the logic. So in this equation of motion, you have the value of m and you have the value of k. So with these numbers, now so this is very basic. I am very sure everyone will understand this. Now for this 3-span box girder, next I want you to determine the natural uh, circular frequency, the natural cyclic frequency, and the natural period of vibration for the longitudinal motion. So this was the first part of the question. Now in the second part, you have to determine, basically you have to determine omega n, Tn, and Fn. This is the natural. Tn is, what is Tn? Tn is the natural period of vibration. Natural period of vibration. Omega n is the natural circular frequency, and Fn is the natural cyclic frequency. So what will omega n be? omega n is equal to under root of k by m. So in the previous question, you had calculated the value of k to be 25,880 and mass was 214.9. So 10.97 radian per second. Now you know omega n. So what will be the time period? 2 pi by omega n. So 2 pi by 10.97. So this is equal to 0.573 seconds. And what is Fn? Fn is 1 by Tn. So 1 by 0.573 is 1.75 volts. Very straightforward. So from this question, we understood how to calculate the stiffness and mass. So moving to the next question. Suppose I have a tabletop like this, right? And this is the x-axis, this is the y-axis, and about this axis, this is the z-axis. Suppose this is a rigid slab. This dimension is d. It's standing, it has like 4 legs, so it's a table sort of thing. So, and it's standing on a rigid platform. You can call this a rigid foundation slab. This is a this dimension I already marked D. This is H and this is B. So here what do you have to do? So it's given that you have a uniform rigid slab of total mass M and it is supported. So you have a rigid slab. The total mass is M and it is supported on 4 columns of height H. So mass is M, height of the column is H that I've written. It is rigidly connected to the top slab and to the foundation slab. Each column has a rectangular cross section with second moment of inertia Ix and Iy for bending about the x and y axis. So columns have a rectangular cross section with moment of inertia Ix and Iy. Okay. You have to determine the equation of motion for this system when it is subjected. So find equation of motion when this system is subjected to is subjected to rotation UG theta of the foundation about a vertical axis. You can neglect the mass of the column. So the only mass you have to consider is the mass of the rigid slab. Mass of the column can be ignored. So I'll help you visualize this rotation g theta. So if let's say this is the z-axis, this is the z-axis, right? This is fine. This is now about this. You have found the rigid foundation slab UG theta. It is rotating. So you can tell that the body is rotating where U theta total, because ground itself is rotating, body will rotate with respect to the ground, so you will have a total rotation term. So for this I want to write the equation of motion. Let's pause for 2 minutes, think about this question, and then we discuss. So here the trick is writing, writing this U theta t. I'll just mention what is this U theta t. U theta t is the total rotation, which is summation of U theta, which is a function of time. What is U theta? It is the rotation of the slab with respect to the ground plus the rotation of the foundation. So using this, and consider there is no damping in the system. Please consider that as well and try to write the equation of motion. Okay. Any ideas how you will start this? How do I approach this question? Again, it is a game of finding out the mass and the stiffness. But how do I start it? Any ideas? Mm, okay. So how do we write such equations? We always tell it should be some mass. We should think like this: M U total plus Ku is equal to 0. No external forces acting here. So here, since things are rotating, rotational mass will come into picture, which is the moment of inertia will come into picture. So I naught, then U total, we'll be using this notation, U t theta double dot. Sorry, this will be with dot. This is the idea. Plus, what will be Ku is basically Fs. So Fs is equal to 0. Is this equation clear? Can anyone confirm or write in the chat box? Is this equation 1 clear? And what will be This I note that is the moment of inertia for this rigid slab. This we already know from our high school physics that it should be m d squared plus d squared by 12. That this is the moment of inertia about the z-axis. This is moment of inertia of rigid slab about z-axis. So is this clear? Am I audible?
Yes, yes, ma'am. Yes.
Yeah, yeah, yeah.
Please.
Okay, okay.
Torsion is the
So once you get this, now I have to write down the expression for Fs. So what is Fs? Fs will be, you will have k into u. So since we are dealing with rotations, I'll write k theta and u theta. Now, what will be the value of k theta here now? So for that, finding the, for that, let's imagine things like that. Suppose this is the slab and I'm looking at the slab from the top, right? I have to find its stiffness. How is how will I how is stiffness defined? So the force required to provide a unit deformation, keeping all the other degrees of freedom zero. Here, all the other degrees of freedom are not there, so it's zero. So you have a slab like this, and I will provide u theta is equal to 1. That is, I will rotate the slab. So I will provide u theta is equal to 1 and my slab will look something like this, right? So when I am rotating my slab like this, suppose u theta is equal to 1, I rotate the slab, the columns will provide certain resistance. So let's consider this column. And this is, if I look at this convention, this is my x direction, this is my y direction. Now, so when you are rotating the rigid plane like this, so in the x direction, there will be resistance in the opposite direction, in this direction. So there will be a force generated. It's a resisting force. Force will be generated in this direction. What will be the value of, and if this is at a, this length is d. So this is at a distance of d by 2. So this force will be kx d by 2. And in the y direction, it will try to bring back the column down. So it's a resistance. So that is ky in d by 2. How much is this? This this distance is b, right? And this distance is d. Similarly, you will have forces generated at all the four ends. So you have a force like this. Now to bring this corner back to its original position in this direction, you will have force kxd by 2, and this you need to bring down, so it will be at ky d by 2. Similarly, your corner has moved here. It has to be moved here. So you need to pull in the x direction and this direction, and in this direction and the y direction you need to push in the upward direction. So k y d by 2 and kx d by 2. Similarly, at this corner, x force is in this direction because this is the new position. You will push and bring it back to the new position, and y is in this position. From here you have to move it back because this is the final, this is the initial. So final to initial you have to push it back, so it will be in this direction. So this is ky by 2 and this is kx d by 2. So what will be the total? Now what is this kx and ky? Kx and ky is the stiffness of the column in that direction, and it's like a it's a column fixed at both the ends, and it is a rectangular column with with moment of inertia ix and iy. So kx will be, so let's assume that the cross section of the column is like this. Ix, this is y. And it's given that the moment of inertia when bending about x-axis, the moment of inertia is ix. When bending about y-axis, the moment of inertia is iy. Let me complete the question here. Ix and iy for bending about x and y-axis. So what will be kx? Kx is the resistance when it is bending 12 e I by height of the column is h, so h cube, and k y will be 12 e I by h cube. Now when you are bending about x-axis, when the column is bending about x-axis, okay, about this axis when it is bending, the moment of inertia is ix, okay, and then the force generated will be in the y direction, that is ky force is getting generated, so that is why this will be x. And when you have to generate kx is force which is generated in this direction. Then in that direction, that will happen when the column is bent, that is, I mean, the column will bend like this. Like if you look at the frame from this direction, let's say, so the frame will look like this. This is the x direction and the column is bending like this. So in that case, which the column is bending about which axis? Can you tell me? The column is bending about y-axis. So that is why y will appear here. I hope this ix and iy is clear. So once you know kx and ky, then I want to write k theta. So what will be k theta? K theta will be basically fs by u theta. U theta is 1. What is the total value of force? The total value of force will be like you sum up all these forces in So kx d by 2, basically I'm taking the moment about this point. And if I take the moment about this point, rotational stiffness. Okay, let's proceed with this and I'll explain this point later. And I'll
Ma'am,
have
ma'am, are we doing static condensation here?
no static condensation. Static condensation is when you have a certain degree of freedom which is not required in a problem. You're trying to remove that degree of freedom. Suppose in a column, in a column like this, you will, what is the kinetic degree of freedom? Not kind of like how many degrees of freedom do you need to describe this? So you will have u1, u2, and u3. But in dynamics, this u2 and u3 is not coming into picture. You just need u1. Then you use static condensation. This is, I'm just finding k theta because that is only that is the only degree of freedom we are interested in. So kx into d by 2, and we are taking moment about this point, so d by 2. And how many such things are such forces are there? Four such forces are there, plus ky into d by 2, and it is at a distance from the center. It is at a distance of b by 2, so b by 2, and these are four such things. So this is equal to k theta. I'll provide a more proper explanation for this. I have a slight confusion in this. So this is equal to k theta, and this is equal to kx into d square plus ky into d square. So now here, if this is the equation of motion, I naught ut theta double dot plus fs is equal to 0. Now this moment of inertia about the z-axis is fine. I naught. Now let's substitute this. U total theta double dot will be u theta double dot plus u ground theta, ug theta double dot plus fs is this term, which is kx d square plus ky d square into, this will be multiplied by, this is k theta into u theta, this will be equal to 0. So I can write this as I naught u theta double dot plus kx d square plus ky d square u theta is equal to minus I theta ug ground double dot. Similar to what we had done for a, suppose you have a frame and you provide a ground excitation, then what will be the effect? P effective was m minus n ug double dot. So on the similar lines, if there is a ground rotation, then things will appear like this. Mm. This is something. Now let's look at one more question. Now in this question, this is question number 4. It's given that a free vibration test is being done on an empty elevated water tank. Suppose you have a water tank. A water tank, you can idealize it like this. Mass is lumped at the top and you have a tank. So free vibration test is done on an empty elevated water tank. A cable is attached to this tank, okay, and it applies a lateral horizontal force of 16.4 kips. So you apply a cable, you have a cable attached to tank, and it is applying and it applies a lateral, the lateral force is horizontal force, which is equal to 16.4 kips, and this force, it is pulling the tank uh, by 2 inches, and this pulls the tank by 2 inches horizontally. So you have a cable, so with this, because of this cable, the tank is moving by 2 inch, and the force which you are applying is 16.4 kips. With 16.4 kips you are pulling it, because of which the tank is moving by 2 inches. This cable is then suddenly cut. You cut this cable, and there is a resulting free vibration, and you have what some observations on the free vibration is given. So you cut the cable and free vibration takes place. Okay. And what are the things observed in this free vibration? At the end of 4 complete cycles, time is 2 seconds. So at end of 4 complete cycles, time is 2 seconds, amplitude is 1 inch. What do you have to find? You have to calculate A, damping ratio, B is natural period of undamped vibration, then C is stiffness, D is weight, E is damping coefficient, F is number of cycles required for displacement amplitude to decrease to zero point 0.2 inch. So you have a tank, an elevated water tank, you pull it with a thread, with some wire, with certain force, because of which there is a displacement of, horizontal displacement of 2 inch. Then you cut the thread and set it into free vibration. And in that free vibration, what is observed? That at the end of 4 complete cycles, the time is 2 seconds and amplitude is 1 inch. Then I want you to find out these quantities. So take uh, 4 minutes and try to solve this question. This kind of question might appear in the MCQ kind of format, or like short questions. So, and then we'll discuss the question after 5 minutes. Take your time, try attempting this question.
Ma'am, could we start with the solution?
Yeah, yes. So,
Ma'am, theta is coming to 0.9.
okay.
Is
Then
it
the
correct?
next one.
So natural period
How much did you get zeta?
0.091.
No. How did you calculate zeta?
Ma'am, first we calculate, ma'am, as per the formula of del is equal to 1 by j ln u naught by u
Okay,
j.
so the formula is zeta is equal to 1 by 2 pi j ln of ui by
Yes, the same
j
formula.
circle apart. Yes.
Yes.
So 1 by 2 pi. This is at the end of 4 cycles. So, okay, what numbers did you plug in here?
So j is 4
Okay, then
and
what
ln
y?
0 u naught is 2 inch
Yes.
and u fourth in fourth cycle it is given 0.2 inch.
No, it's 1 inch.
Okay, it's 1 inch, sorry.
So
So
if
now,
you plug in the number, you will get 0.027.
okay.
So it's 2.7%. Right. So this is the uh, damping ratio. Then how do I calculate the time period?
TD is given, ma'am, 2 by 4.5 TD is given.
Yes.
So there is a one relation between TD, TN, and zeta.
So
So
TD, how will I calculate TD? TD is in 2 seconds, it can complete 4 cycles.
yes,
TD is 0.5 seconds. Now, TD and TN are related. So but damping is small. So omega D is equal to omega N under root of 1 minus zeta square. Are you talking about this relation?
yes, ma'am. Yes.
So this can be written as 2 pi by Tn under root of 1 minus zeta square. This is 2 pi by Td. So Tn is equal to Td under root of 1 minus zeta square. So can you plug in the value of zeta and calculate Tn?
Yes.
Point 5.
Td is almost equal to
Almost, ma'am.
2.
Yes.
Yeah. So the next question is, how do I calculate the stiffness? How do I calculate the stiffness?
Stiffness.
So, yeah, any idea? So
Omega
you,
squared
Is
is equal to K by
and
L.
Wn is root under uh,
hmm,
Wn is equal to root under k by m.
hmm,
So Wn, we know Wn,
hmm.
we know the mass.
We don't know the mass.
No, we have something. No, 16 point. This is what?
That
Okay.
is the force.
Okay.
So what is stiffness? Stiffness is F is equal to K into X. Stiffness is the force which is required to produce unit deflection. So here you know when you pull by 16.4 kips, your displacement is 2 inches. So from there I can calculate stiffness. So stiffness will be 16.4 kips. When you pull by 16.4 kips, it sorry, it moved by 2 inches. So this comes out to be 8.2 kips per inch. Is this clear?
Yes,
Yes.
ma'am.
Okay. So the next is, so this is done, this is done, this is done. Now I want to calculate the weight. Now what you were suggesting, we can use that K is equal to M omega n square. Then M will be K by omega n square. K is 8.2. And what is, can someone calculate what will be the value of omega n? Omega n is 2 pi by time period. 2 pi by, so 4 pi if you substitute it here. So can anyone calculate what is the value of mass? So it will be this number. You can plug in the numbers and you can find, right? So can anyone tell me the number so that I can compare?
Oh,
0.05.
Yeah, and be sure what units you're working in and what units have been. If it's an MCQ kind of question, what kind of unit is given in the answer? Some kind of unit conversion might be required. So weight is that. Then how do I calculate damping coefficient? Damping coefficient means C. How do I calculate C?
zeta root under 2 km.
Yes, so C by M is equal to 2 zeta omega n. We can use this for what you suggested. So from there, if you calculate C, suppose I want to use this formula, zeta is 0.027, omega n is 4 pi, and mass would be this number, 8.25. So pi whole square. So this will come out to be 0.036 kib second inch. And this should be done. Then can you tell what is the number of cycles required for the displacement amplitude to decrease to 0.2 inch? So again, let us use this formula that damping ratio is equal to 1 by 2 pi j ln of ui by ui plus j. Now I have to calculate j, that is number of cycles. So 1 by 2 pi. What is theta? We already know that is 0.027 from here. And at the beginning, at the first cycle, your ui, let's say u1 is equal to 2 inches. And what do you want? After, you have to find after how many cycle it decreases to 0.2 inch. So this 0.2 inch will appear here. So that is the amplitude that is occurring after jth number of cycles. And you want to calculate this number j. So if you solve this, this will be equal to 13.28 cycles. So this is how you calculate the last part. That is the number of cycles required for the amplitude to decrease from a certain number to a certain. Now, in this question, suppose that the weight of the water which is required to, now till now the tank was empty. It was an empty tank. Now suppose I fill water into this tank and the weight of the water is 80 kips. You have to determine the new natural vibration period, Tn, and the damping ratio when the tank is full. So suppose I add water to the tank to fill it. In this process, the rate of water is 80 kips. Determine natural vibration period and damping ratio when tank is full. So here what you are changing is the weight. Initially, what was the weight? You calculated the mass. Here you calculated the mass, right? And the mass was equal to 0.0519 kip seconds square per inch. Suppose I have to calculate the weight. Weight is m into g. So g is 386 inch per second square. So 0.0519 into 386. This comes out to be 20.03 kips. So what is the new weight? The weight of the empty structure was 20.03 plus you are adding water whose weight is 80 kips. So the weight of the structure is changing. So is there any change in the stiffness of the structure? No. So when the weight is changing, this weight becomes 100.03 kips. So time period is 2 pi by omega n, 2 pi by under root of k by m. So what will be the new mass? New mass will be this 100.03 divided by g, 386, whole divided by what is the stiffness? We already know the stiffness here. Stiffness is 8.2 kips per inch. So 8.2 kips per inch. And this comes out to be 1.147. Then I have to calculate the damping ratio. So any idea how do I calculate the damping ratio? Or will it change? Or will it remain the same? So I can use C by M is equal to 2 zeta omega n. Now omega n is changing, so zeta has to change. Will C remain the same or change? C won't change because you are changing the mass of the system. How will the damping how will the damping coefficient change? It won't change. So zeta is equal to C by 2n omega n. C is what you had found earlier, 0.036. 2 into m will be 100.03 by 386, and omega n again you can calculate under root of k by m. So k by 100.03 with 386. So if you solve the numbers, it will be 0.0123. So is this part clear? Okay.
Yes.
Okay. Let's move on to the next question. Suppose I have frame like this. This length is 16. Force P applied, and U is the degree of freedom which I'm measuring. Then in this frame, I have a friction device attached to it. The angle of elevation of this brace from the horizontal angle is alpha, and this is a friction device. So you have a small building. It consists of 4 steel frames. So this is the elevation which I have drawn. If you look at it from the top, it is something like this, and you will have steel frames on all the 4 sides. So you have 4 steel frames. So this is the RC slab sitting on this frames, and the weight is W. And it is given that uh, the normal force across each of the spring-loaded friction pads, it is adjusted to be equal to 2.5% of the slab weight. Meaning, suppose if I want to draw the variation of the friction force, this force P with respect to U. So it's given that the normal force the normal force across each of the spring-loaded friction pad is adjusted so that it is equal to 2.5% of the weight of the slab. If the normal force is this, we know that friction force, what will be the friction force in the device? Friction force will be some friction coefficient mu into the normal force. So mu and the normal force is 2.5% of the weight. So 2.5 by 100 into W. So mu into 0.025 into W. So if I plot this force P versus U, so this how will that friction force look like? Since it's a friction device, this you might have seen such a diagram in the lectures. So this slip force, this is equal to mu, the value of this force is 0.5. It is equal to 0.025 W into mu. Okay. Then it's given that record something like this is also given. Here on the x-axis we have this is a 0. In this axis, suppose you have time in seconds, and on the y-axis you have u in inches. And suppose it starts from a point here where it is 5.5 inches, then it undergoes um, at this point, the y coordinate is 0.1 inch, and the x coordinate, the time is 4.5 seconds. Right? With this record is given. This is a record of this building. It's freely when there is free vibration along x-axis. So this diagram shows free vibration of building along x-axis. You have to determine the effective coefficient of friction. That is, you have to find this value of mu. Find value of effective coefficient of friction. Yeah. So assume that all the weight that is participating, it is because of the rigid slab. The columns are not participating, and only there is energy dissipation only because of this device. There is no other source of energy dissipation. So first, which you can find is what is the value of time period. Can you find what is the value of time period? Looking at this free vibration plot, I'll just tell that
4.5 by 9.
by 4.5 by 9.
There are 9 cycles, no?
Yeah.
And 4.5
So,
time is 4.5 second takes to complete 9 cycles.
yeah. So if you start from here and you end here, that is how one cycle is completed. Here, if you count, there are 9 such cycles. So the time period would be in 4.9 seconds. 9 cycles are getting completed. So the time required for one cycle will be 0.5 seconds. Fine. Now, can you calculate what is the value of UF? That is, how much is the decrement in the value of the notation of the values in the class. So for UF being, when we studied why define UF, can anyone define UF in context of when we studied Coulomb damping, Coulomb damped free vibration? What was that is when there is a linear decay, when we move from one peak to another peak, the amplitude decreases by 4 times UF. What was this UF?
F by K.
F by what? Like, what will be the force here in this context? Or if let's just use the definition. If I want to use that definition, if I want to use that fact which we had derived there, that is when you move the decrement, uh, like the when you move from peak ui to ui plus 1, there is a decrement in the amplitude by 4 uf. This is the fact which we had uh, derived. I'll just draw that.
Slope of the graph.
This no, it will be, if that is the slope, then why is this factor 4 into coming into picture? So we have derived that thing, that the differences between this peak and this peak is 4 uf. So can I use this information in this plot and calculate the value of uf? So 4 uf. So here it is 5.5. Finally, it is 0.1, and the decrement is happening over 9 cycles. So I can tell that the total, mm, or if you want to think in this manner, 9 are the there are 9 cycles. The difference between two consecutive peaks is 4 uf. So the total drop from 5.5 to 0.1 will be this total number, and this is equal to 5.5 minus 0.1. So from here you can calculate the value of UF to be 0.15 much. I hope this UF calculation is clear. Any doubt?
Yes, yes,
You-
clear.
Then any idea how we will calculate this value of mu? This is the friction force in the in this friction device. So in what will be the friction force along each brace? If this friction force along this direction, if it is here, it is given that P is equal to 0.025 weight into mu. If you have this value of P, can you calculate its component along the brace? That will be the friction force along each brace, right? So the component of P in the direction of the brace will be you know the value of P, right? The friction force along each brace is known. What is this? What do you have here? So I have the value of UF. Then if I can somehow uh, relate UF like you were telling, UF is equal to F by K. I know the value of UF. I know the value of, do I know the value of K? I I can calculate K because I know what is the value of time period, right? And I can write K is equal to N omega N square. What is mass? Mass can be written as W by G. and omega n can be written as 2 pi by time period, so 0.5 seconds square. So from there I can write stiffness. So if I have these two numbers and if I can get the value of F, then I can calculate the value of mu. Now the friction force along each brace is the number which has been given to you. So along each brace, the friction force is mu into 0.025 into W. So if I draw one brace, this angle is alpha. Friction force along one brace is this. What will be the value of, I should not name this S. Suppose this is FB, FB. So because of one brace, what is the horizon, what is its component in the lateral direction?
F cos
So,
alpha.
so FB, that is the force in the brace, cos alpha. Now, how many such horizontal forces will you have? You will have four such horizontal forces. So you do four. So FB is mu 0.025 weight component cos alpha into 4. So if you plug in the numbers, you will get what can I find the value of cos alpha here? So here cos alpha will be 16 by what will be this diagonal? This diagonal will be 12 square plus 60. How much is is equal to this is under root of 400 is 20. So cos alpha is 16 by 20. So let's substitute cos alpha here. 16 by 20 into 4. So this comes out to be 0.08 mu into W. And can anyone tell why do we have this factor 4?
Due to four bracing, each bracing have four. Each friction device have four bracing, no?
But you have two frames in the x direction. So you have one frame which you are considering is this frame and this frame. Since the free vibration of the building is like along x-axis. So there are two frames which I just highlighted. And on each frame you have these two braces. This brace and this brace. So in total, there are four braces in a direction, right? In this frame, you have this brace and this brace. So from each brace, you have this FB cos alpha. So two braces here, two braces here. So total four braces. And suppose you get the value of F. So UF will be 0.08 mu W by K. K is this number which I want you to substitute. And UF is 0.158. So if you plug in the numbers from here, you will get the value of mu, right? And you can do it afterwards. It will be equal to 0.767. And, is this clear? Is this question clear?
Yes, ma'am.
This, any doubt in this week's content? Lot of things were covered. I'll try to cover
Yeah,
them in the
this
next class.
week was really a lot of content was covered in this week.
Yeah, there were a lot
So,
of yeah. So any
ma'am,
particular
mostly all the time, not a single topic. I got understanding. I got complete understanding. This.
so
If we talk
did
about equivalent viscous damping, rate independent, the, all these
rate
things are.
independent rate independent was the thing which you had studied earlier, Coulomb damping. It is it is a rate independent. The friction force. What is friction force? You just had mu into n, so it is not rate independent. But when you're thinking about the viscous damper, the equation is c into, it's dependent on velocity, so it's dependent on the rate of change of displacement. So that is one thing. And what problem did you have in equivalent viscous damping?
How
Any
to how we are calculating this equivalent damping to-
See, the entire idea is you're just equating the energy, uh, the energy in the hysteresis plot. Suppose, like, when do we do it? So, for uh, for dealing the damping damping is a extremely difficult phenomenon, and it is not well understood till now. So what can be the sources? How can a object lose energy? It can lose energy through, suppose you have a pendulum, you just swing it, and it is, what will you observe? It will come back to its rest position. It will move, and with every cycle its amplitude will go on decreasing, and finally it will stop. So what was the why did it come back to its initial position? There must be some, that it lost its energy. Now why did it lose its energy? It lost its energy because of air resistance. Now suppose that pendulum, you're hanging from a certain a joint. Now at that joint also there will be some that rubbing, that is that pendulum bob is hanging, suppose, with a thread. Now the thread is attached to a hook. Now that thread will move like this against the hook, and there will be a rubbing. So there will be some energy dissipation there. Similarly, there can be other forms of energy dissipation also. Like this is some example which I give you. Now in a building also, like there can be, suppose there is a reinforced concrete building and some earthquake hits, there can be various sources of energy dissipation. There will be cracking in the building, that in that way, that can be a source of energy dissipation. Or so it is a difficult phenomena to put it into numbers. We introduce the concept of viscous damping. So when do we use the concept of equivalent damping? Suppose in the lab you do a certain test and you draw the hysteresis plot, and you come up with
Ma'am, what is hysteresis plot exactly? Was
yeah,
this
yeah, I'll just. So what we are doing here is the dynamic hysteresis plot. The structure is remaining elastic because of the nature of the force. The body is dissipating energy, and you are just plotting with you. You are plotting the energy dissipated. That is, if you are thinking about viscous damper, what is the force in the damper? The force in the viscous damper is equal to C into D dot. So if you plot that, so this, let me call this FD. If I plot that, your plot will look something like this. And if that you have a spring mass kind of system, suppose you have a spring as well as damper, then what will be the total energy dissipated? It will be because of the spring as well as the damper, but uh, because of the spring, there is no energy dissipation because the stiffness, this is constant, right? It is linear elastic. So your loop is just rotating. So this loop, basically, this loop is known as the hysteresis loop, or you can tell the area which is enclosed uh, by a curve when you plot U versus FD, which is FD is the energy dissipated, that is known as the energy loop. So that is known as the hysteresis loop. Suppose I do an experiment in the lab and I record this energy dissipation with you, and I come out and I know that my energy dissipation is something like this. Suppose for this system, for this unknown system, I have to find, for this unknown system, suppose I have to do now, I have to do maths and I have to write the equation of motion. Then I need to know what will be the value of zeta. How much zeta should I consider? To calculate that, I compare this unknown system. Let's say, like in place of this unknown system, had a viscous damper be had the damper been a viscous damper, or had the source of energy dissipation been a viscous damper, then what will be the value of zeta? So when we are comparing the two systems, we are equating the energy dissipated. So basically what we are doing, we are equating this area with respect to this area to calculate the equivalent zeta for this unknown system. This is the entire idea of the equivalent viscous damping. That is, for this unknown system, what will be the value of viscous damping? So this is very clear.
Okay.
And regarding the math, Newmark beta central difference and those things, that we'll do separately. Putting it inside this class was not possible. So, did you understand the Duhamel integral portion?
No, ma'am. No, no.
So, let's briefly, if we can
Yes.
discuss that, because using this that Duhamel integral, the response to arbitrary forces like step forces, ramp
Yes.
forces, we can write those equations. We'll start that. We'll not be able to finish that. We'll take up from there and do the numerical equations. So we will do the response to uh, arbitrary forces. So here the concept of impulse is discussed. So what is impulse? Impulse uh, is defined as force into time. Now, what does Newton's second law say? Newton's second law says that rate of change of momentum is equal to the force applied on the system. So d dt of, what is momentum? Momentum is mass into velocity. Rate of change of momentum is equal to the applied force. Now, suppose the mass becomes constant, then I can remove the mass from this derivative, and this will be d dt of u dot is equal to P. Now, m d dt of u dot is u double dot into T. Now, suppose I want to take up this equation, and suppose I bring dt on the right hand side. So t dt is equal to, suppose you have m d u dot, and suppose I want to integrate this equation from t1 to t2, from t1 to t2. Now this term on the right hand side, which is integral of force into time, this is basically impulse, and this is equal to m is constant. Then what is the velocity of the body at time t2 minus velocity of the body at time t1? So this impulse is nothing but it is equal to m into delta u dot. Now suppose you have a force acting on the body, and the force is like this. It is arbitrary. What we are doing here is, let's say, we consider at a point, at a time t, the value of force is a certain number. Let's say this is equal to pi. What we are studying here is, had this portion and this portion and this portion not been there, and at a time t, just there is just a force pi, what will be the response? This is what we are trying to study. There what we are telling, that suppose at, let's say, uh, a certain time, you have a certain impulse, and the value of the impulse should be 1. Now, what is impulse? Impulse is force into the time over which it is acting. Let's say the time over which it is acting is epsilon. So, to keep the product to be equal to 1, the value of the force should be 1 by epsilon. This is epsilon. This is 1 by epsilon. Why this is 1 by epsilon? Because what is impulse? Impulse is duration into the value of force. I want the value of impulse to be 1. That is how I get this number. Okay. Now, and this is, when is the impulse applied? The impulse is applied at the time tau. Okay. At the time tau, impulse is applied. The value of impulse is 1. The duration over which the impulse acts is epsilon. And since the value of impulse is 1, the value of the force should be 1 by epsilon. Right? Now let's consider this. Now we will be applying this to a single degree of freedom system. Let's assume that the displacement prior and up to the impulse, that is u tau, is equal to 0. Now let's use this fact that impulse is equal to m delta u dot. The value of impulse is 1, mass is m. What is the final velocity uh, at u at this point, u dot tau, and let the initial velocity be equal to 0. So u dot tau is equal to 1 by m. So the initial conditions are established, that u at tau is equal to 0 and u dot tau is equal to 1 by m. Now suppose you have a single degree of freedom system and this impulse is active. So, first I want you to recollect this, and suppose there is no damping. So n u dot plus k u is equal to 0. So for what would be the solution of this equation? The solution of this equation will be Does anyone remember the solution? It will be u0 cos of omega nt plus u dot 0 by omega n sine omega n. This solution is fine. This we had done. We were trying to find the homogeneous solution. We assumed
Yes,
that
yes.
the solution would be e to the power lambda t, and then we had found this solution. Now just substitute the initial conditions here. U of 0 is 0, so this term goes away. U dot 0, like 0 in the sense I'm referring to the time tau, because at that time tau only the impulse is acting. So u dot 0 is 1 by m. Then you have this omega n sine of omega n. Then why I am writing t minus tau? Because before that time, like this function will exist only when t is greater than tau. When t is less than tau, this force is not present only. So here there is no existence. That is why I wrote the term t minus tau. So this response, which I just wrote, it is known as the unit impulse response function, and it is given the name ht minus tau. So ht minus tau is equal to 1 by m omega n sine of omega n t minus tau. So basically, when a unit impulse acts on a single degree of freedom system, its response is this, and that is why the name unit impulse response function. This is given the name unit response impulse function. And this is true when t is greater than tau, because when t is less than tau it is not there, and when t is uh, and this is for when there is no damping present in the system. Suppose when there is damping present in the system, then this is damping. Suppose there is damping present in the system, then you should start with mu dot plus u dot plus ku is equal to 0. So for that, ut will be equal to e to the power zeta omega n t u0 cos of omega dt plus u dot 0 plus zeta omega n u0 by omega d sine of omega dt. Now again here if I substitute the initial conditions, e to the power zeta omega n t, this will be there. Then we have, so in place of t, you will have t minus tau, because this will exist only when t is greater than equal to tau. Then u0 is 0, so it goes away. U dot 0 is 1 by m. Again, this term is 0, this term is 0. So m by omega d sine of omega d t minus tau. So now this is when damping is present in the system. So with this information, suppose this is for when there is one impulse force. Now, suppose the force acting on your body is something like this, which you actually have. It is like a arbitrary force. So T with respect to time. And what you have just written here, it is say result due to at time t you are taking this value as d tau. So for you have the value for this one impulse. If you can add the results because of all these small impulses, suppose I divide the force into small parts, that will be the response of my single degree of freedom system to this arbitrary force. So what would, and since the body is linear elastic, what for when there is unit response, when there is certain only one impulse acting on this body, what is the response? H t minus tau. That will be your the response. When you will have this in place of unit impulse, suppose you have this is the value of impulse. What is the value? Let's say it is p, the value at tau. So what will be the value of the response? The value of the response will be this t minus tau, that function into p tau. That will be the value of one impulse. Now, if I can sum up the value of all these impulses over over the entire time period, and where the value of each impulse is d tau, this will be the total response. And this is when you add it, TUT. That will be the total impulse, and it is true only when t is greater than tau. If I'll give an example, you will get this better. Suppose I take the system. I take the example of a step force. So what is the step force? Suppose I have this mass. There is no damping on the system. Suppose is K. The force is P of T. And suppose this is the degree of freedom. The stiffness is K. And the force acting is like this. At T is equal to, like when T is less than 0, it is 0. Then the force increases to P naught. So P of T is equal to P naught. Okay. Now, suppose I want to use Duhamel integral here. How will I use Duhamel integral here? Duhamel integral, I'll have to use this expression. How do I use it here? So let's use this expression here, that u of t is, t should not be there. U of t will be equal to, what is the value of p as a function of time? P naught. And what is h? What is that h? That is the unit impulse function. Unit impulse function is this. Just use it here. So I'll just write for your convenience what is the value of ht minus h, that is the unit impulse response function when there is no damping. It is 1 by m omega n sine of omega n t minus tau. Now u of t will be, use this. P of tau is P naught. H of t minus tau is 1 by m omega n sine of omega n t minus tau. into t tau. You integrate it from the time 0 to t. Now, if I integrate it, it will be equal to p naught by m omega n. Integration of sine is minus cos omega n. Now, here you will have to do this substitution. That is, you cannot directly integrate it. Take t minus z is equal to some new variable. That is, t minus z is some new variable t1, then t minus tau. My pen is t minus tau is some new variable, let's say t1. So t minus d tau is equal to d tau 1. Then d tau is equal to minus dt1. So if I substitute it here, it will be sine of omega n. T minus tau is t1, minus d tau is minus dt1, when tau is equal to 0, t1 is equal to t, and when tau is equal to t is equal to 0, then you can write p naught by m omega n. Because I have the minus sign, I can reverse the limits. Sine of omega n t1 dt1. So t naught by m omega n integrating omega n t1 by omega n 0 to t. So t naught by m omega n square, upper limit is cos of omega n t, and cos, suppose I keep the minus sign outside, cos 0 is 1, then this will be p naught by m omega n square is k, then I have 1 minus cos of omega n t. So this p naught by k, we often use the term ust naught. Ust naught, 1 minus cos of omega n. Omega n can be written as 2 pi by time period into t. See what the answer which we got earlier with the classical technique which we did earlier. From that also you will get the same expression. This is just a bit convenient because you have this h unit. What is the name? Unit. I keep forgetting the name. Unit response impulse function. If you use this unit response impulse function and do this integration, you will directly get the answer. I'll also use the classical method and I'll show you, we'll get the same answer. With the classical method, what will be your equation of motion? Your equation of motion will be mu dot plus ku. What is the force acting on the system? P naught. Now, what will be the your solution will be summation of complementary solution and particular solution. So u will be u complementary plus u particular. What is u complementary? This we already know. This will be uh, u complementary is solution of mu naught plus ku is equal to 0, and solution of this is u is equal to A cos of omega nt plus P sine of omega nt, right?
Yes.
And what will be U particular? U particular will be nothing but the
P naught
force
by
P
K.
naught by K. Because if you substitute it back here, double derivative of this is 0 and K into P naught by K is equal to P naught. So left hand side is equal to right hand side. It is satisfying the differential equation. So your total solution will be A cos of omega nt plus B sine of omega nt plus P naught by K. Now, how do I calculate A and B? I'll use the initial conditions. So, what are my initial conditions? That here, what are the initial conditions? Let's assume, like, if the system is initially at rest, so at U is equal to 0, so U0 is 0 and U dot 0 is also equal to 0. So if we use this here, you will find that your A is equal to minus P naught by K and B is equal to 0. I hope figuring the initial conditions is fine. You'll be able to figure it out. Like, how did I calculate it? Since I'm doing it, it's just finish. Yes. U is equal to this. So let's put T is equal to 0. So at U of 0 is 0. So this is 0.
Ma'am,
Mhm.
but in this case, this P naught is acting continuously, na? And in
Yeah.
the
So P
so
will be
here
continuously.
from 0 to T only, na? Here the P naught is acting from 0 to T.
No, this is
Okay, this
not
is a
taking.
continuous.
This
Okay.
is continuous. This
Okay.
is
Okay.
not that case.
Acha.
This is not this case.
Okay. Okay.
It's not the rectangular pulse case. Now I'm considering this classical example.
Okay.
So A and plus P naught by K. So A comes out to be minus P naught by K. And when you do the velocity, that U dot is equal to A omega n sine of omega n t minus plus E omega n cos omega n t. And then you substitute t is equal to 0. This comes out to be 0. So b is equal to 0. So when you substitute a and b back to this u, so u is equal to minus p naught by k cos of omega n t, b is equal to 0, and then you have this p naught by k. So your solution is p naught by k 1 minus cos omega n t. So whether you do with this classical approach or you use this Duhamel integral. Duhamel integral is when you use this ht of t minus tau, this unit impulse response function. You get the same answer whether you use this technique or this technique. You can see these two are the same. So it's just technique of reducing that. So, okay, so I think so. Can you tell me when is your examination?
Ma'am, it is scheduled on 26th April.
Okay, then surely we'll have the next class before that. And there I will cover the ramp forces, step forces, and the remaining part where lots of other things were covered in the last week material. I'll try to cover that. And
Okay.
in the time being, if you are solving questions, if you have any problem, please drop an email. My email ID is skany8k21 at the rate itk.ac.in. And we'll again, most probably we'll again meet next week. I'll try to arrange an extra class and to finish your
Okay.
session.
Okay. Sure.
Okay,
Okay.
okay. Thank you for attending
Thank
this
you, ma'am.
session.
Thank you.
Yeah, I'll close the session.